about, are the two systems exactly the same or they are different? For example, and there is a standard for the forced choice method. I don't know what this method is, I've never used it. But the reason I'm displaying this table to you is that when you come across a problem, please don't just assume PSNR is perfect and will solve the problem for you. It depends on the type of problem. You have to use your brain and look in the literature. On exam, PSNR will come almost certainly, unless there may be a question which will say, what kind of error measure would you think we would propose for it? And then that means I'm sampling your brain. I want you to say something, clever, something that we've all discussed. Is it a good error measure or not? So one way to measure quality is a subjective assessment. So PSNR is objective. There is a formula, you put numbers, and you get a result. Think about it. Imagine this PSNR is based pixel by pixel. So for example, if I take a picture and move it to the right by 1 pixel, every pixel will be different. So the PSNR will not be great. But we just moved a pixel, an image, by 1 pixel. You probably not notice. So this really is a pixel-based stuff. It's the best we can do. But if this error here, there are 2 large errors. Imagine you have a scene like that in a television, you're projecting me a lecture in the television. If these errors appear somewhere on the wall, probably doesn't matter that much. Maybe you won't even notice them. If these errors, these pixel distortions appear somewhere in a critical part of text, you may not be able to see it. If they appear on the face of an actress or an actor, you will not like it because it will really affect your experience. So that's why we have subjective, and subjective means we have people, we have subjects, and they look at it and they say what they think. Do you think the quality is excellent, good, fair, poor, or bad? So how you do it? So you basically switch between the reference picture and the coder, and the coded picture, decoded picture, by showing people the reference picture, decoded picture, then they vote, then you show the reference picture, coded picture, they vote again, and there are even standards for that, how long you do. So 10 seconds voting, 10 seconds reference, 3 seconds, you show the gray level to kind of erase a bit, and then you show the coded picture for 10 to 15 seconds, and then you give them 10 minutes to vote, 10 seconds to vote, and it's picture number 1, picture number 2, picture number 3, and people are just pressing excellent, good, fair, poor, bad, and then you average over a large number of people, and that's the result. Very often, this kind of studies are done by the MPEG group, by the codec development people, and so forth, by television channels. This is something I want you to be aware of, is that the sensitivity of our eyes is not flat in terms of spatial frequency and the temporal frequency. So what is the spatial frequency? The spatial frequency is basically the texture. You think about zebra, it's got quite a lot of lines. So how many of these lines per unit of certain unit of angle? Are there 5 lines or are there 20? That's the spatial frequency. And the temporal frequency is how frequently something is flashing in time. So if you look at 1 pixel, it might be going black and white, like this. So how frequently that happens. So as you can see, this is the sensitivity contrast. What it means is that the sensitivity contrast means the the value, this change that you have here, related to the maximum value of the signal, that is necessary for us to see it at all. So what that means is that there are some frequencies, temporal frequencies and spatial frequencies, that we are more sensitive to, and there are some of them that we are less sensitive to. And that's simply the way our visual system works. So some frequencies we are more sensitive to. Why is that? Probably because of the thousands of years we had to escape from tigers and other animals, and certain frequencies were more important for us to do that. In the same way as our hearing is designed for a certain frequency range, that there is a core range where we have the best ability to distinguish. So obviously, this PSNR does not understand the frequencies, temporal or spatial. It just looks at single pixels. It cannot appreciate that certain things are more visible to us than other things. So quite often in video coding, image coding, we take this into account, and you will see that in JPEG as well. So the contrast sensitivity is how much do we need to change the value with reference to the background intensity in order to see the difference. Okay, so if I've got the background, the 251, how much do I need to change that? By how many in order to see? So if this contrast sensitivity is 0.1, that would be, I have to, for 251, I have to change it by 2.5 pixel in order for anybody to even notice the difference. This here you have an example of frequency. So this is frequency, spatial frequency. There's a DC here, which means the entire screen is with the same gray level pattern. And as you increase the frequency, you will see more and more of the stripes. And here you have K, which is how much we've changed the intensity here with respect to the background, which was, say, 1 to 8. So as you go here, you can see less and less change. And maybe you'll notice that at some point here, you stop seeing any difference. You say, here it's the same, there's no change. Well, there is a change, but just this contrast is less and less. And depending on the frequency, you can see here something like that, which means that for higher frequencies, you can actually see with less contrast. There is a less contrast here as we go up. That's just how our eyes are. Okay, very good. So let's now get into the business of coding of street pictures. So what kind of tricks we can use to code these pictures? Well, first of all, we might be coding pixels individually, of course, but we might try to do some transformation. What do I mean by that? Do you remember this example I gave you at the very beginning of a lecture when I asked you to encode a sinusoidal wave, send it from A to B? And somebody here said, well, if it's a sinusoidal wave, I don't need to send it values like crazy every second or every millisecond. I can simply say, it's a sinusoidal wave, this is the frequency, this is the amplitude, and then the trick is done. So in fact, this is an example of a transform domain. We transform the signal from one domain to another domain. And a typical example of a transformation from one domain to another domain to time domain is the Fourier transform, okay, which you probably heard of before and maybe learned before. And maybe you didn't really get a very good feel. I remember me being a student when I kind of, there were a lot of formulas and I kind of understood mathematically the formulas, but I didn't get a feel. I mean, what does it do? what is this frequency domain? Why is it called a different domain? And we'll have a closer look at that during this lecture so you get a better feel of the transform domain. But essentially, on a very, very basic level, this is the trick that we've done there. That if something is behaving like a sinusoid, rather than sending a lot of values, we just say it's a sinusoid of that frequency. Okay, but we know that signals in real life are not just sinusoids. They're not generated by sinusoidal generators. Well, they are not, but actually they are typically a combination of many different sinusoidal signals. And that goes actually quite deeply into the nature around us, because, for example, quite often sounds originate from something resonating. Okay? So if I drop my phone somewhere, if you analyze the sound, there will be some bass frequencies there, which probably have something to do with the resonating frequencies of this basic setup, this phone dropping. Of course, when you take any instrument, you usually have strings. These strings resonate, and therefore the music that is produced is just a combination of many, many different frequencies with different amplitudes and phases. Okay? So in the transform coding, we would be doing precisely that. So in the spatial domain, we really go, we don't perform some transformation, we look at the pixels here, and we try to code them. But of course, we know that there is dependence. If I pick any two neighboring pixels, they are likely to have similar intensity levels. So I somehow want to account for that fact, for the fact that the neighboring pixels are related. So how can I do that? Well, in a very, very simple way. For example, if I want to do it in a lossless way, because I'm expecting neighboring pixels to be the same, I can define my codebook by some string of symbols that, I apologize, that's a different slide. Let's first talk about lossless coding in spatial domain, okay? So here we have an image, and here we have some symbols in that image. What are the symbols? The symbols are the gray level values. But here I'm just showing A, B, C, D, E. Now, if you look at the distribution, the probability distribution, you will find out it's not flat. There are some most likely values that exist in images. There are around maybe 200 gray level value on quantization 0 to 255. So it's not flat. And we know that the entropy of that is better than the entropy of a flat distribution. We know we can use that to lower the number of bits in a lossless way. So one trick we can do, we can look at the probability by plotting histogram. So if you have an image, how many times we have A, B, C, and D, or how many times we had 251, 252, 209. It would be a longer histogram, of course, with 255, 256 values, but we would have a histogram. This histogram would represent the probability distribution. And the trick would be to assign short codes to something that is seen very frequently, that the probability is high. So you remember I asked one of you, how would you code, what code would you assign to something that is occurring very frequently? This is occurring very frequently, so we gave it code 0. Now, because we gave it a code 0, nothing else can start from 0, because there would be a confusion. So now I have to start with 1, so all of them start with 1. Now I can choose another one to have 1, 0. Well, the second most frequent is C, so it's 1, 0. So these two have to have 1 here in order to be different, and now I have to distinguish between these two, so I gave 0 here and 1 here. This is just kind of ad hoc way. I'll show you a better way to do it. So what we can see here, we gave, normally we have 4 symbols. 4 symbols means 2 bits per symbol. Now, what I have here, I have 1 bit for B, so I'm gaining. 2 bits for C, so I'm not gaining versus if it was flat. And I have 3 bits, which I have more, for A and D. So I'm hoping that A and D is so infrequent, happens so rarely, that it won't happen very often that I need 3 bits. And I hope that B, as I see here, will come very often, so very often I need 1 bit. So overall, I'm good. That's the idea of lossless coding in a spatial domain. Okay? So, we can also do that in the conditional way. So what we can say, right, what was the previous symbol? Depending on the previous symbol, because I have 4 symbols, A, B, C, and D, so the previous symbol can be only one of them. Previous symbol means previous pixel. So if I go to the previous example here, you know, we kind of notice that B, after B, always happens B, right? Quite frequently, okay? So there is some dependency of that symbol on that symbol. Well, I can now say, if the previous symbol was A, what is the distribution? If a previous symbol was B, what is the distribution? And so forth. So now we did this trick, and what we see is that these distributions are now changing. So if the previous symbol was A, the B is most frequent. But if the previous symbol was B, A is more frequent. And here C, and here D. So I can do the same trick as I did before, but I can condition it on a previous symbol. That will increase the performance of my method. And this is actually quite often done in image coding, in video coding. I can also group pixels. I can say, well, I will be coding 4 pixels at a time. What is it going to do to the size, to the number of symbols? If, in this particular case, I have 4 symbols, A, B, C, D, right? So how many different combinations for 4 of them? For a block of 4. Think about it like this. You have 4 possibilities here, A, B, C, D. You have 4 possibilities here, A, B, C, D. 4 here and 4 here. So for this block 4 by 4, how many possibilities? 4 to the power 4. Yeah. Yes, it is. Yes, because if you think you can build a tree, you can say, oh, I can give 4 here. Now from each of these 4, I can give 4 to the next one, and from that I can give 4 and can give 4. So it's 4 to the power 4, which is, have your calculators ready? 4 to the power 4 is 16 times 16, which is 256. So quite a lot of symbols. But in an image, we just said we might have 256 different values. So if I did this trick on images, I took 4 pixels, and each of them can have 256 values. How many different possibilities I have there? You are so happy you answered my question. So next is coming now. All right. So for 4 pixels, 256 values, what do we get? 256 to the power 4, which is, now it's a bit of a more serious number, right? I'm kind of puzzled. Why does it take people 2 months? So, okay, so what is the number?
4.29 to the times 10 to the power of 9.
So he got something to the power of 9, which is probably correct. very, very large code book, probably too large, certainly too large. Okay? But for fewer symbols, we can do that. So what we are doing now, actually maybe in this example, we just blocked 2 of them. So we have IA, AB, AC, AD, and so forth. And here it would not be to the power of 4, it would be to the power of 2, but still a large number. But we can do that. And then the other trick that we can do, so the tricks we mentioned is we can block group in spatial domain. We can take 2s, we can take 4. We can take them horizontally or vertically. For images, do you think taking horizontally would be better or vertically?
Horizontally.
What would that depend on?
The orientation of the image.
Kind of.
On the south.
Yeah, I think it would depend whether there is more correlation like this between the pixels or more like that, right? If the pixels tend to have lines like that, it might have to do with the, I don't know if you look, for example, if I look at this classroom, I can see a lot of lines like this, but maybe it's just this lecture theatre, otherwise you'd see something different. Right? So it really depends what you are trying to code. Right, now, this is a trick that happens very, very frequently, which is prediction. So what is prediction? So prediction is a very simple thing that we try to guess the next symbol, given the past symbols, and then we subtract, we calculate the error of our prediction by subtracting our prediction from the actual value. And we only code the difference. We code the error. So what does it do to the distribution of our signal? I would like you to now work in a group for 45 seconds, so it's a time constraint problem, and I would like you to think about this. If I have an image, like this one, but bigger, this is my probability distribution of gray levels. So between 0 and 255. What happens if I now say, right, I'm predicting that pixel here. I'm guessing that it will be the same as the value here. The next pixel is the same as the previous one. Is it a reasonable guess? Well, look at everything around here, okay? If I took this pixel and took this pixel, is it a reasonable prediction? Probably yes. If I take this pixel and this pixel, yeah. If I take this pixel and that pixel, well, that's not reasonable because this one was white and this one was black. But overall, things tend to be, except for edges and things like this, pixels tend to be similar. So we can predict the next pixel using the previous pixel, or we could predict the pixel, we could predict this one from here, or maybe we could predict this one from here as well, or maybe we can have some other prediction. But what I would like you to now do is think about it and try to sketch the probability distribution. This is the probability distribution of pixels in an image. What will be the probability distribution of the difference between the next image and the previous image? Okay, 45 seconds. Please work in groups.
No, probability. Probability.
At the moment, no.
The biggest symbol below, so we don't use it goes away.
Please work together.
Hard, flat.
Turn back and take part in discussion.
With them, I mean, Are we talking about symbols in general? Yeah, just in any given limited number of symbol system. That's what it's saying. If you move from showing symbols themselves to showing delta between two symbols, you expand the number of values you have to send, and you have almost twice the number of symbols.
Yeah.
Yes, the majority of
Think of an example.
Oh,
Well, that is.
Yeah, but I was just thinking, like, you know, if we have to use current values
honestly, I'm not. I don't know.
I don't got much feel for it.
Sorry?
It's still
Very few pixels is down to the error structure with the minimum quality. So you get lower probability if it would be minus alpha. The next is between 0 minus predicted to 5.5 and 0 minus 2.5 will be 0 minus. The max is the error 5.5.
Right. Okay.
Because it's like worse.
This from this diagram.
Next, but actually 2.5 is 0 minus 2.5, so it's minus 2.5. Yeah. Probably. I don't make a mistake of
what it's saying is that you move from 6 to predict what the next one is. That's the prediction. So if it's that minus, so effectively it's always the delta between the two.
So how's it going? What do you think?
So it is like.
It's like a black magic a bit at the moment,
Yeah,
or,
so if you get
or you have some ideas?
your assumption is the
like
next
a
one will
Gaussian
behave as
that's
well.
minus between minus 2.5 and
Not, but
2.5.
it's better if you use
So
them
it will be
because
something
there is actually a
that
difference
is
between them.
centered
So
around
if it's
0.
1, 2, and 3, and 4.
Possibly, if our prediction is good, it will be very peaky.
Your prediction is the next pixel will
So guys, so
also-
we are thinking about predicting this pixel from that pixel, okay? So if our prediction is perfect, if these pixels are the same, then the difference is 0, right? Prediction is perfect. So it's going to be a peak somewhere here at 0. This will quite often happen, that the value that we predicted is correct. But occasionally there will be pixels where, you know, it will be, this was white and this was gray, and sometimes even it will be that it was white and it was black. So depending whether we go from white to black, we might come up somewhere here, or from black to white, we'll come up somewhere here. But statistically, it will be some kind of distribution which will have a strong peak in 0. Strong peak assuming our prediction works. Okay, if we do poor prediction, then it will not be 0. But if our prediction is good, means quite often we hit the right target. We predict 5, it's 5. So the difference between the prediction and the true value is 0. We predicted 5, it was 5. We predict 8, it was 8. We predict 9, it was 8. Okay, minus 1. We'll have a peaky distribution. What do you know about the distributions that are peaky in terms of lossless coding? What is the entropy of a peaky distribution?
Is it the same? Is the limit of the codec? So entropy of the slower.
Entropy is lower, right? Perfect. And entropy being low means that we don't need so many bits to code. So hey, great, exactly. We are changing a distribution which was not so peaky into a distribution that hopefully is very peaky, which means we can code losslessly with very little bits. And the better our prediction, the better our coding, the less bits we use. But of course, the truth is, prediction is never perfect. Is it possible to predict the entire image from the first pixel? If we could predict the entire image from the first pixel, we would only need to send the first pixel, right? And the guy on the other side could predict the rest of the image. So how do you know that we can't predict the image from the first pixel? Can we code the image? Can we guess the image from the first pixel? Well, we can very easily build a contra argument. I can certainly make two images that have the same first pixel and look completely differently. I can construct these images, right? I can take two images here, and then paint shop the first pixel to be the same, if they are not the same, but the images would be very different. Of course, just by looking in the first pixel in the image, we cannot guess what the image contains. It's not possible. So we know we cannot have a perfect prediction. But maybe for the next few pixels, we can do that. And so the encoder, what the encoder does, something comes in here. This just remembers the last symbol. So the first symbol, there is no prediction. It just goes here, and the next symbol comes in, but this is the previous symbol. It's subtracted from the next symbol. So it's a fancy way of drawing really that there is a memory. Here is the memory. It just remembers the last symbol. It's one symbol that it subtracts it from the original symbol. And then it goes back to the memoryless coder. So this codec, this is some way of encoding. We'll be looking how to do it based on the entropy coding. And of course, you can have more sophisticated ways of predicting. So you thought about predicting from the previous pixel, but we could predict that pixel from any combination of these pixels here. We tend not to predict from that pixel or that pixel. Why?
Because you haven't got them yet.
We haven't got them yet, right? Because when we send the image one by one, when we arrive here, we usually scan all of them and arrived here, but we don't have these pixels here, so we can't use them for prediction. But if we use different scanning, if we were scanning image like that, then we could use the different pixels. But of course, we can only predict from the pixels that we have. Well, that's not precise statement because we have all the pixels being encoder, but the decoder hasn't got some. Decoder only sees what I've already sent him. So when I'm encoding, predicting this one, the assumption is I've already sent this one to the decoder. So the decoder sees everything up to this point, but doesn't know these pixels yet. So sometimes we have these exam questions that I'm asking you, what is the best way to encode X? Is it X equals C? Is it X equal B or X equal A? And I give you an image. And I'm asking you to check that. And one way to do it would be just to look which prediction minimizes the error. So if I said predict X from A, you would just see what is the difference between these neighboring pixels, and if it's C, you would take the difference between every of these pixels and the pixel on the top. Which one gives you smaller error? Okay, very good. There is also something called run length coding. Run length coding means if symbols tend to repeat, we could say how many times we repeat each symbol. So this is really only appropriate to a source that tend to repeat the value, okay? But it's a very powerful coding. So we would code, for example, which symbol is it and the number of consecutive repetitions of that symbol, which we quite often call run. And then we say, okay, so we had symbol A 3 times, symbol B 4 times, symbol C twice, and so forth. And you will see that then later how it's how we use the practice. So now, entropy coding. We've already mentioned it. The idea is, how do we assign shorter symbols to something which is happening more frequently? How do we do that? And there are two approaches. One is called Huffman coding, and one is called arithmetic coding. The Huffman one is very easy to implement, but it's not always optimal. The arithmetic coding is an optimal in some sense, and it really can approach the entropy. And it's quite frequently used in practical applications. By the way, it's a very interesting story because the arithmetic coding was patented by IBM about 35 years ago, and now the patent has run out. So there was quite a lot of issues with that because it was a very powerful and good progression. Okay. So how do we code? How do we do half-one coding? So there's more than one way to do it, and as long as they will not all produce the same mapping between symbols and numbers, but they will all produce the same entropy, the same efficiency. So let us assume that I have 4 symbols, A, B, C, D, with probabilities, associated probabilities 0.5, 0.25, 0.15, and 0.1. Now, you remember, we want the symbol that is most frequently repeated, is the highest probability. We want this symbol to have a short code. That means that the symbols that have low probability, we want them to have a longer code. Okay? So we order the symbols from the one that has got the lowest probability here, D 0.1. Then the next one is C 0.15, D 0.25, A 0.5. In this particular case, it's not a very good example because the example should start with a different combination. But here they are already ordered like this. This one is the highest probability, this one is the lowest probability. But if not, you can reorder it. So you want to have them here, where the lowest one has got the lowest probability, and the top one has got the highest probability. Okay? And then what you do, you just combine the 2 lowest probabilities together. So C and D you combine, and you say, okay, 0.15 plus 0.1 is 0.25. And you compare it with the next one here, or all of them. You don't want to be, so if this one is above that one, you just draw a line here and you go to the position where it's supposed to be. So if that was 0.3, you would be here because you want to be between 0.25 and 0.5. And if it was 0.6, which it can't be, but let's assume it was more than that, this line would go here. But because these two are equal, you can leave it here. You combine them, these two together, so 0.25, 0.25 is 0.5. And then you combine these two together, and you get probability 1.
Does it matter which one gets a 1 and which one gets a 0?
It does not, as long as you agree that with between the encoder and decoder. So it's up to you to decide, and normally the way it would work is that you would do this design in the lab, so on a piece of paper, and then you would implement it in the software. So you have to make sure that the encoder and the decoder are using the same mapping, meaning that, for example, here you could say, right, if I go up, it's 0, if I go down, it's 1. So here, up is 0, down is 1, up is 0, down is 1, up is 0, down is 1. But you could have the other round, up is 1, down is 0, or you could even have non-consistent approach, and you could say, well, I'll just drop a coin, now I want 1 up, 0 down. It does not matter. But of course you want to be consistent just for simplicity of checking. So here we are consistent, we have 0 on the top, 1 on the bottom. And what we see this, that to get here to A, we have just symbol 0. To get to B, we first here to go down and here to go up. So it's 1, 0, 1, 0. From here to get to C is 1, 1, 1. And to get to D is 1, 1, 0. So these are the codes generated. So please note that because we started here with the lowest probabilities, and because we link this, we build our tree so that we start linking from the lowest probabilities, the tree becomes longer to get to these ones here. Because I link this to first, I link this to next, and so forth. So to get here, I have to use this symbol here to decide how do I go here, and this symbol here, this symbol here. So these symbols because they were at the end of the cube, they have the longest symbols. C and D, you can see, has got the longest symbols. Okay? So, what I would like you to do now is this. I would like you to work in groups. I would like you to work in groups and design a half-hour codec for this source. So the source has got symbols A, B, C, and D, and the probabilities are as follows: 0.8, 0.1, 0.08, and 0.0. Please work in groups. And please use this assignment. When you go up, you go 0, when you go down 1, so that we can then do a little interoperability test between groups. So I'll remind you, you have to, actually, can I please change something? I made it a bit too easy for you. So it's going to be, here it's going to be 0.02, and here it's going to be 0.08. Or no, I'll make it even more difficult. Okay? Please work actively during the lecture, because it's your opportunity to learn it for the first time, and then by the time you revise, it will be the second time. Your brain will accept it easier, and this very frequently comes up at the exam, because this is something that you don't really have to learn anything really in memory. It's very, very logical that, you know, you build a tree and you have to start with the lowest probabilities one for this tree to be longest for these ones.
If the lowest one
Yes.
were B and D, let's say,
Yeah.
would we rearrange them so that they're next to each other, or would we kind of just draw this upward line that crosses C? If that makes sense.
Say it again.
So if B and D were
Yeah.
the two lowest ones,
Yeah.
would we rearrange the
Yeah.
letters so that B and D are next to each other so we can link them more easily, or would we just
You
link
would,
them and then the line for C would kind of like go through the thing?
so if you have a situation that at the moment the lowest probabilities are B and C,
Yeah.
right? So when we sum them up, it's exactly the same as D.
Yeah.
But if that was more than D, we would jump over D. Is that your question?
But maybe it's
Okay, I would, maybe
Maybe
if
I
you
would
can
just
draw
draw
it,
it,
yeah,
yeah.
if you draw it, because I don't want to answer the question wrongly, because there's misunderstanding. Yes.
I have another question.
Yeah.
Does it make sense to then use, because in this case I'm not using, for example, the one symbol twice, so I'm not using just one, I'm using 0 and then it's 1, 0. I'm also using 1, 1 or 0, 0. Does it make sense then assign those longer symbol to the shorter one, like in order to make it more concise, especially when you have like a lot of symbols and it grows really fast in the number you need to represent them?
I'm not sure. Do you mean that we
Yeah, I
don't
mean,
that we don't have 0 followed by something here?
Now that after I do this, I just, something else that says that I is just 0, B is 1, and then C would be, I don't know, 0, 0, and D is like 0, 1, to like shorten the length. I need to represent the symbols.
You cannot really shorten it, because to have the unique symbols, you need to have a tree when you walk around the tree and you arrive at some end nodes.
Yeah.
If you don't, you cannot stop here and have a symbol here, because then you would not know whether a run of symbols generated that symbol or with the following symbol
Yeah,
generated that
yeah,
symbol.
but what I'm sort of saying is like encoding those like those sequence of symbol in saying, oh, the sequence 1, 0 correspond just to 1 to like make it shorter. I don't know if it makes sense.
Oh, apply apply again on this one.
Yeah, sort of like.
Apply.
Then I guess
You could do that, but I don't know whether we are not already saturated, but we probably could do that. So what we could do, we could then say, right, now if we look, let's say if we have more of the symbols and we have some complicated things, we could say, right, how about if we represent 1, 1, 0 as another symbol and apply arithmetic coding again? Yes, we could do that. There's nothing to prevent us as long as there is a unique encoding and decoding.
Okay.
But
Just
I can't say whether that would bring
efficient.
a very big benefit, but maybe it would, yes.
Right, so if B and D are the least probable, then we kind of end up with like them two being summed together, and then C is kind of in the middle, so that we kind of draw it like this, because that looks really
So
awesome.
yeah, so what we do,
Or do we rearrange them?
we
to draw
arrange
the-
them.
Okay.
We arrange them. So
So we kind of list them in the probability order, if
yes,
that makes sense? Okay.
exactly. So when you list these numbers here, the important is this probability order, not whether A is followed by B and all this. So if say A was the lowest, least likely, say 0.05, A would be here. Okay, we would have B, C, D, A. Okay, so everything is based on probability.
Wait a minute.
But rearrange them. Okay, rearrange it so you get the same code.
Ah, so this one.
You can do that. Yes.
How can we not charge these rates as zero?
Yeah.
As we go, how can we charge for 131, let's put that in 0.8.
Yeah. Okay. So what you do, you collect the lowest two ones, the B and C, connect them together,
Yeah.
and then at the end of this, yeah. Click on the yes, and then when you connect these two, what is the probability to that one?
It's 0.1.
Exactly. Right point one.
Yeah.
Okay. Is that point one now in the right place? So the next one on the top above that is what?
I don't even know this is.
Okay, so it's still alright, right? It's not more than that, okay? So now you connect this point one with the next point one. Okay? And what is the probability there?
It will be 0.1.
I'll do that by mistake before I draw lines from down.
Point two. Okay, right, point two. Okay? And
I
then
realised I have to
connect
read
that
off
one
this as well.
with A, with the next one on the top. Alright? Yes, but I don't want this line to protrude that. When you connect something with them, because otherwise you have more lines than you can see, okay? And now you start from the final line.
Yes.
The one,
Oh, you haven't drawn it?
This one, yes, and
Are we
you
drawing the?
go back, and if you go up, you put one,
Spot.
if you go down, you put
That
two.
is right.
I have A, D, B, C. Yeah.
Or other way around, if you go up zero, it doesn't really matter as long as you Great, so now if you look at it,